What if I told you there's a computer so powerful it can solve in seconds what would take today's best supercomputers millions of years? Welcome to the mind-bending world of quantum computing, where particles exist in multiple states and calculations happen on an unimaginable scale. In this video, we'll break down how quantum computers differ from the traditional machines we use every day, why it matters for everything from finance, and how this emerging technology could change your life sooner than you think. Hit that subscribe button as we make the complex simple, the future clear, and your knowledge unstoppable. 1. The basics of traditional computing. Traditional computers operate using bits, the smallest unit of data that represents either a 0 or a 1. These binary digits process instructions sequentially, creating predictable and reliable outputs. Classical computers rely on transistors to switch bits on or off, controlling data flow. Every task, from typing a document to running complex simulations, follows this binary logic framework. Software languages, operating systems, and applications are all built around this foundation. Moore's law has driven progress, doubling transistor count on chips over decades. 2. The quantum bit, qubit. Quantum computers use qubits, which can exist as 0, 1, or both simultaneously through superposition. This unique property allows quantum systems to process massive amounts of data in parallel. Qubits are realized using subatomic particles like electrons, photons, or atoms. Quantum entanglement links qubits, allowing changes in one to affect another instantly. These properties make quantum computing fundamentally different and exponentially more powerful for certain tasks. However, qubits are extremely delicate and require ultra-cold, controlled environments to remain stable. 3. Speed and processing power. Quantum computers can solve specific problems dramatically faster than classical computers. They process complex calculations by exploring multiple solutions simultaneously. Traditional computers must analyze each possible solution one at a time. Quantum advantage emerges in problems like factoring large numbers, simulating molecules, or optimizing massive systems. Algorithms like Shor's and Grover's exploit quantum properties to accelerate computations. 4. Error correction challenges. Quantum systems are highly susceptible to noise and errors due to environmental interference. Qubits easily lose coherence through heat, vibration, or electromagnetic radiation. Error correction in quantum computing is vastly more complex than in classical systems. Traditional computers use redundancy and checksums to detect and fix errors. Quantum error correction codes require entangling multiple qubits to protect information. The overhead needed for reliable, fault-tolerant quantum computing is significant. Scientists are developing new algorithms and hardware designs to improve qubit stability. 5. Encryption and cybersecurity implications. Quantum computing poses both threats and opportunities for cybersecurity worldwide. Powerful quantum algorithms can break widely used encryption methods like Rives, Shamer, Adelman swiftly. Traditional encryption relies on factoring large prime numbers, which quantum computers excel at. However, quantum cryptography introduces new security protocols like quantum key distribution. These systems leverage quantum properties to detect eavesdropping instantly. Governments and businesses are racing to develop post-quantum cryptography standards. 6. Applications in healthcare and medicine. Quantum computing holds enormous potential to revolutionize healthcare and drug discovery. It can simulate molecular interactions and protein folding at unprecedented scales. Pharmaceutical companies can accelerate drug design and testing with quantum models. Complex genetic analysis and optimization of treatment plans become more feasible. Personalized medicine benefits from processing massive biomedical datasets efficiently. Quantum-enhanced imaging and diagnostics could improve disease detection accuracy. Epidemiological modeling and public health strategies gain precision with quantum analytics. 7. Transforming artificial intelligence. Quantum computing enhances artificial intelligence and machine learning capabilities significantly. Quantum algorithms can accelerate training of large-scale models rapidly. Optimization problems in AI, such as neural network tuning, become more efficient. Pattern recognition and data classification improve with quantum parallelism. AI models handling vast, unstructured datasets gain speed and accuracy. Hybrid quantum classical machine learning systems emerge as a powerful approach. Quantum computers can simulate complex cognitive processes and decision-making systems. 8. Quantum cloud computing. Due to their complexity and cost, quantum computers are often accessed remotely via the cloud. Major tech companies like International Business Machines Corporation, Google, and Microsoft offer quantum computing platforms online. Researchers, developers, and businesses can experiment with quantum algorithms without owning hardware. Cloud services democratize access to cutting-edge quantum technology globally. Hybrid architectures integrate quantum and classical resources for real-world applications. Quantum cloud ecosystems foster collaboration and innovation across industries. Users develop, test, and deploy quantum software through cloud-based toolkits. 9. Hardware and technology race. Global competition is intensifying to build scalable, fault-tolerant quantum computers. Companies and governments invest billions in advancing qubit technologies and architectures. Approaches include superconducting qubits, trapped ions, topological qubits, and photonic systems. Each technology offers trade-offs in coherence time, error rates, and scalability. Research institutions and private firms race to achieve quantum supremacy and advantage. International collaborations and open-source platforms accelerate breakthroughs. Standards, benchmarks, and interoperability frameworks are under development. 10. Future of quantum computing careers. The rise of quantum computing creates exciting new career opportunities across industries. Demand grows for quantum software developers, physicists, and algorithm designers. Interdisciplinary roles combine quantum physics, computer science, and engineering. Quantum educators and communicators bridge the knowledge gap for broader audiences. Policy experts and ethicists guide responsible development and deployment of quantum tech. Quantum cybersecurity specialists protect data in a post-quantum world. Businesses seek consultants to integrate quantum solutions into operations. Thanks for exploring the incredible universe of quantum computing. With us, where the impossible starts to look possible. We've just scratched the surface of how qubits, entanglement, and superposition could transform everything from cybersecurity to drug discovery and artificial intelligence. If you want to stay ahead in understanding the technologies that will shape tomorrow, make sure you hit that subscribe button and join our growing community. We break down the most complex innovations into simple, actionable insights every week. And remember, turn spare change into crypto profits. Here's how, because mastering tomorrow starts by preparing today.